It's just about 20 years since the famous voyage of the raft Kon-Tiki, on which the young Norwegian ethnologist Thor Heyerdahl, with a crew of 4 Norwegians and a Swede, sailed or drifted 4,300 miles across the Pacific on the Humboldt and on the South Equatorial Currents. Heyerdahl set out to establish that Polynesia could have been colonized by refugees from pre-Inca Peru. But apart from the archaeological interest of the expedition, what sticks in the mind most is this picture of the strong, steady current reaching its way out across the Pacific. But if the early Peruvians knew enough about currents to use them, their counterparts on the Atlantic seaboards don't seem to have been so alert. We didn't hear anything serious about currents until the 18th century. In the 1760s, Benjamin Franklin was Deputy Postmaster General for the colonies. He discovered that ships sailing between Falmouth in England and New York, mostly British mail packets, took 2 weeks longer to cross the Atlantic than merchant ships sailing from London to Rhode Island, although the routes were almost the same length and there shouldn't have been more than a day's difference. Franklin discovered from his cousin, a whaling captain from Nantucket, that the Rhode Island sailors knew about the great eastward flowing current called the Gulf Stream. On their westward journeys they were taking care to avoid it, whilst on their eastward journeys they made use of it. British sailors didn't know about this trick. So Franklin and his cousin set to work. They tracked the Gulf Stream and made measurements of its speed, and after some years the first chart of the Gulf Stream was issued to mariners. It's a good deal simpler than today's version. We've learnt since then that the Gulf Stream is a very complicated mass of water. Since Franklin's day, we've got more familiar with the currents, and we recognize them all over the ocean. Apart from the Gulf Stream, moving up from Florida past Cape Hatteras, there's the Labrador Current coming down from the Arctic, carrying icebergs past the coast of North America. Across the other side of the Atlantic, on the west coast of Africa, there's the Benguela Current. And the exactly equivalent current off the west coast of South America is the Humboldt Current that carried Kon-Tiki. In the northern part of the Pacific, there's the great clockwise drift of the Kuroshio Current. And in the Indian Ocean, there's the Somali Current. Finally, the Antarctic Circumpolar Current completes our general picture. Already, this provides a complicated pattern of water movement. Because masses of water of different temperatures go to different parts of the globe, they must obviously be considered in any studies of climate, of the distribution of animals and plants, and of course of shipping routes. In fact, currents have become the focal point of a considerable field of oceanographic research. Is there an overall pattern in their movements? What drives the currents? How do they relate to the other physical phenomena of our planet? To answer some of these questions, we've got one of the world's experts on ocean currents. He works at the National Institute of Oceanography in Surrey, and he's Dr. John Swallow.
Although the strong surface currents have been well known to sailors for hundreds of years, it's taken a long time to build up the general picture of the circulation, and even now, many features are still obscure. You can get a better idea of what is happening if we put in more detail on this chart here. This is roughly the pattern of the world's surface currents. The thicker arrows indicate where the currents are strongest. All these surface currents are driven by the prevailing winds, and if we superimpose the wind pattern on the current patterns, there is some correspondence. The currents tend to follow the wind except when they're deflected by land, but the relationship between the currents and the winds is not a simple one. To begin with, although the winds are fairly uniform, the currents are not the same strength. You'll notice a tendency for strong currents to lie on the western sides of the oceans. Here, for example, is a strong Gulf Stream, here the Kuroshio, here the Somali Current, always on the western side of an ocean, and they tend to be associated with closed loops of circulating water. This tendency for currents to be stronger on the western side is an effect of the Earth's rotation. Anything going round with the Earth takes part in the anti-clockwise spin, and the amount of spin varies. It's anti-clockwise in the northern hemisphere. The amount of anti-clockwise spin that you have depends on where you are on the Earth's surface, greatest at the poles, least at the equator. So if a bit of water starts here, and it is moving round southwards in this clockwise loop of current. As it moves southward, it finds itself having more anti-clockwise spin than is needed for its new latitude due to its position on the spinning Earth. And this anti-clockwise increase in spin balances against the tendency of the westerly winds here and the northeast trades to impart clockwise spin to the water. But when a current is going north, on this side of the Atlantic, of the North Atlantic, the winds are still producing a clockwise tendency, but in addition, the water gains clockwise spin by changing its latitude from south to north. So in fact, it gets a double amount of clockwise spin. And this can be balanced by anti-clockwise spin introduced by having a strong boundary current against the western side, which can create enough friction in its eddies to impart anti-clockwise spin to balance the clockwise spin imparted by the winds and the northward movement on the Earth's surface. There is another effect of the Earth's rotation, which is a small force acting at right angles to any body that moves on the Earth's surface. This is known as the Coriolis Force, and it's quite important for movements on a large scale in the atmosphere or in the ocean where other horizontal forces are small. In ocean currents, the Coriolis force acting at right angles in the northern hemisphere is balanced by an equal horizontal force due to the banking up of water on the right-hand side of the current. I'm speaking of the northern hemisphere again, water is banked up on the right-hand side of the current to provide a pressure gradient which balances this Coriolis force. And in fact, in a current situation like the Gulf Stream, we find that looking along the current, you have warm water piled up on the right-hand side of the current. And the Gulf Stream is, in fact, a boundary current running along the front between a banked-up mass of warm water on its right-hand side, filling the whole loop of current in the Sargasso Sea in the central part of the North Atlantic, and the cold water to the north. Of course, our chart of surface currents is only a very simplified one, showing the average situation of currents, and there's a lot of complicated detail left out. For example, the Gulf Stream has many streaks of fast-moving water, some of them moving as fast as 5 knots. And these are embedded in slower-moving streaks or even countercurrents, and these are continually breaking up and changing their position. And when the Gulf Stream gets out into deep water, it doesn't run straight, but goes in large loops or meanders. And this meandering isn't due to the wind, but to the unstable nature of the current itself. Eventually, some of these loops sometimes get sufficiently exaggerated to break off into eddies. South of the current, an eddy will be a patch of cold northern water rotating anti-clockwise. And some of these cold patches can last for as long as 6 weeks, gradually drifting off to the south. North of the current, a loop forms a patch of warm southern water rotating clockwise. And sometimes these warm loops have been seen to persist for as long as 3 months. In fact, the Gulf Stream is a very complex current. Further across the North Atlantic, although the average picture of a branching current is maintained, the current divides not so much up into branches as a number of disconnected fragments.
All we've looked at so far are surface currents, but the ocean's deep, between 10 and 20,000 feet deep. How far down do these wind-driven currents persist, and are there deeper currents? What do we know about them? Surface shipping must pay attention to surface currents, and submarine shipping must pay at least as much attention to submarine currents.
The answer is that the strong currents aren't very thick. At 1,000 feet down, they're only a fraction of their surface speed. But there are deep currents, but they aren't produced directly by the wind. They depend mainly on the density distribution. The way that currents decrease downwards depends on this distribution of density and how it varies from place to place. The density of the water in the sea can be varied in different ways. In low latitudes near the equator, the surface water is heated and that reduces its density, but partly that gets offset by evaporation, which leaves more salt in the water left behind. In high latitudes, either Arctic or Antarctic, the surface water can freeze, and again salt is left behind. And at the same time the water is very cold, and it can become dense enough to sink through into the deeper layers. So we have the ingredients of a deep circulation system driven by these density differences. But finding out what's going on in the deep water isn't so easy as it is on the surface. We can't rely on ship's observations for measuring these deep currents. Until recently, the only effective ways we've had of looking at what's happening in the deep water has been to take samples and measure the properties of the deep water. Here you see water bottles being lowered into the sea on a wire, each of them carrying reversing thermometers. You have about a dozen bottles separated at different depth intervals in a line at one time. Here a messenger has been released to reverse the first bottle, and that releases another messenger which trips the next one, and so on. Here you see the string of bottles being brought back on board and returned to the laboratory for the samples to be drawn off. In the laboratory, the thermometers are read and the water samples drawn off from the bottles that have collected them. In the Royal Research Ship Discovery in the Indian Ocean, something like 27,000 water samples were collected. And all of these were analyzed for various chemical properties of the water: salinity, dissolved oxygen content, and various important nutrients. And that was the work done on just one cruise of one research vessel. And there are many dozens of research vessels going on cruises all the time. The first thing that one finds from looking at the distribution of temperature in the water is that most of the water in the ocean is really remarkably cold. Under the equator in the Atlantic, the temperature drops from about 25 degrees centigrade at the surface to 10 degrees at 1,000 feet down and 5 degrees at 2,800 feet down. And at the bottom, the temperature is only a little over 2 degrees centigrade. Now, although we have such a great mass of cold water, yet the surface water is being heated by the sun's radiation, and the heat is coming in from the bottom, very weak source of heat from the interior of the Earth. So why doesn't the whole of the water column warm up? What's happening is that the cold, dense water that sinks in north and south polar latitudes spreads from these deep water sources through the whole of the world's oceans. And as the deep water spreads, it has to rise to complete the circulation. Here you see a chart showing the distribution of temperature at a depth of 13,000 feet in the Atlantic. It shows the warming of the Antarctic bottom water, which is originating in the Weddell Sea at the southern end of the Atlantic Ocean, and this water spreads slowly northwards through the Atlantic, increasing in temperature as it goes. It's warmed by heat flow from the seafloor and by warmer water mixing into it from above. If we'd taken a somewhat less deep level, like 10,000 feet, we would have seen the water moving southwards from the North Atlantic, spreading in the opposite direction to the Antarctic bottom water, to the south through the Atlantic Ocean. This would have been shown best by plotting the distribution of dissolved oxygen. And one can use salinity as another tracer for plotting current movements. Looking at these spreading water masses, we get a general impression of the direction in which they're moving, but no idea of their speed. One way of getting at the overall speed is by measuring the carbon-14 concentration in the deep water. The decrease in carbon-14, radiocarbon, as it moves northward in the Pacific, suggests that the deep water spends about 1,500 years in the Pacific away from the surface. In the Atlantic, it seems to stay there only about 500 years. And these lifetimes of the deep water in the ocean suggest that the average currents in the water must be about 1,000th of a knot.
We've arrived then at a general broad picture of the deep water circulation, mainly from examining samples of water brought up from different levels. Thousands and thousands of samples taken over the years by all the world's research ships. But to try and understand how these patterns are set up, there have been many attempts to build analog models. At the Lamont Geological Observatory in New York, Dr. Ichie has been using a rotating tank experiment to try and investigate the behavior of the Great Southern Current that runs around Antarctica. The idea is to try and see how deep cold water from an Antarctic source could spread out, first into the Atlantic, and then, after running along in the current, into the Pacific. A dye is used to trace the water movement, and the dilutions adjusted from time to time. The temperature difference between the pole and the equator is simulated with electric heating elements around the outside of the tank. Gradually, the current pattern develops. And over recent years, a whole series of experiments has been carried out in a big tank at Woods Hole. Here they use neat-looking rubber continents and carefully simulated winds and differential heating effects. Various ocean basins have been studied in this way, including the Antarctic waters and the source of the deep cold water supply. Some of the effects can be seen very well in time-lapse film. Of course, these models are flat discs, not globes, and the detail on them is bound to be limited. But leaving them and leaving the charts we saw earlier, how close can we get to a theoretical model of the global circulation?
The way that the deep water moves certainly isn't as simple as we might suppose from the way we can see the water masses spreading out. There are many possible ways of moving the water around and arriving at the same distribution of properties, and the simplest way they could move is not necessarily the most likely one. One of the leading workers in this subject, the American oceanographer Henry Stommel, has worked out the dynamics of a model of the deep flow which supposes sinking to occur in two places, one in the extreme North Atlantic and one in the South Atlantic in the Antarctic, with a slow upward movement from the deep layer everywhere else. And allowing for the Earth's rotation, he could show that there should be western boundary currents in the deep water just as there are on the surface, although they're not always in the same direction. In the Atlantic, for example, he showed that there should be a deep boundary current going southwards all the way down the western side of the Atlantic, right through from north to south. There's some evidence for a deep western boundary current in the Atlantic, both from direct measurements and from observations of temperature and salinity in the South Atlantic. We expect these deep boundary currents to have speeds of a few tenths of a knot, and these are the kind of speeds that we have observed in the Atlantic. However, there are short-term fluctuating currents in the deep water, not just on the western boundary, and going even faster than a few tenths, and these have been observed by direct measurements.
These direct measurements that can be used to check on theoretical models are obtained by very ingenious techniques. One of the best known and most useful ones was in fact devised by Dr. Swallow himself. The instrument itself is a free float, a cylinder designed to ride vertically in the water at a predetermined depth. When the float reaches its depth setting, it emits a signal that allows it to be tracked by its mother ship, so that the direction and the speed of the current, if any, can be measured. Floats sent down to different levels from the same spot can reveal currents moving in totally different directions, possibly identifying a deep countercurrent below the surface current.
But even this kind of direct measurement raises more problems than it solves. If measurements are taken at the same spot at different times, there may be wide variations in the results. These are some of the tracks and speeds of floats recorded to the west of Bermuda some years ago. From the 13th to the 17th of April, a float moved southwestwards at a depth of 6,000 feet at a speed of 9 centimeters a second. 5 centimeters a second is a tenth of a knot. Another float laid on the 15th of May at the same depth moved in a clockwise loop to the northeast at 11 centimeters a second. Yet another float laid at the same place on the 18th of June moved at 5 centimeters a second to the northwest.
The floats have proved then that there's a lot of variation in the direction and the speed of the currents, but they've also proved that the currents move at quite a good speed, so it's now possible to use more economical means to measure them. Several groups are experimenting with anchored current meters that stay in one position for some time, and we found that one of the most interesting experiments was going on at the Woods Hole Oceanographic Institution at Cape Cod in Massachusetts. The director of the experiment is Dr. Nicholas Fofanoff.
The purpose of the program of current measurements is to measure the variability in the ocean. The fluctuations that are observed reflect the mechanisms and forces acting on the ocean. A current meter placed at a single point in the ocean determines the variability in time, and the variations range from a fraction of a second to slow fluctuations that range over weeks and even months. These fluctuations also occur with depth. Current meter placed at a different level will record a different range of fluctuations, and so measurements must be taken over a series of depths at a point. Furthermore, there are variations with location. A mooring with current meters set some distance away will record still differently, and therefore measurements must be made over space as well as depth and time. Now, it's all very well to say this, but the organization required to carry out this work is rather complex and consists of at least 3 separate parts. First of all, the instrumentation and mooring must be engineered for reliability, for endurance, and for the precision necessary to take the measurements. And secondly, ships and personnel must be available and organized to take these moorings and instruments out to sea, to set them on location, and to recover them and bring them back. And finally, the data that's collected must be analyzed and interpreted for the dynamical mechanisms that we are looking for.
Several moored current meters have already been sent down on an experimental basis. A buoy carrying a radio beacon is the top end of the system. The radio is for the retrieval of the equipment. The next piece down, quite a bit lower on the line, is a digital temperature and pressure recorder. At this stage in the experimental work, one of the problems is to find out how much equipment can be put down on a line and how the whole system will stand up to the drag of fast currents. Woods Hole itself is inconveniently close to the edge of the Gulf Stream, which will sweep away most buoys. Next comes the current meter itself, recording both the speed and the direction of the flow. The rest of the equipment on this line is acoustical gear that allows the whole line to release itself from the bottom on demand. The last thing to go down is the anchor. At this stage, only one current meter is moored below the buoy, but it's possible to set up several of them on the line at different levels, and even to create an array over a wide area with a number of moorings. The current meter records its data directly onto tape for the computer, but as a precaution, and to check the equipment, a film version of the recording can be monitored.
First few frames. Perhaps there's piles of weed. Oh, here they are. Suddenly it seems to be working all right.
Well, let me make note of that bad section.
Now, the speeds are very high, though. The rotor 1 channel is completely jammed. We'll have to use just rotor 10s.
In the normal way, all that has to be done is to prepare details of the experimental runs of the current meter for processing by the computer.
About 20 of these probes are will be used for decoding the other 10.
Without the computer, the number of calculations involved, even in a trial run, would make this kind of project quite impossible. Of course, the computer itself has already been programmed to deal with the data, sorting out the current flow from, say, turbulence around the meter, allowing for tides and other regular fluctuations. Finally, presents the material in a form which allows relatively easy visual interpretation. Running the data processing and interpretation end of the project is Dr. Faith Webster.
The kinds of measurements that physical oceanographers have classically collected have enabled us to formulate several models of how the ocean currents are constructed. Some of these have been very helpful for formulating models of the ocean. An example is the 12-hourly tide. Here's a picture of what measurements made at one of our buoy locations showed for a period of 10 days from the 8th to the 18th of July. They show a nicely developed 12-hourly tide rotating around twice a day for this whole 10-day period. An examination of what was going on at the same location, both before this 10-day period here and after the 10-day period, shows that in fact the 10-day period which we just saw was in fact not typical at all of what was going on at this location. That before this time there were areas where the speeds were very high, times when the speeds are very low, times when they're high and low again. So the speeds themselves are variable, the directions are highly variable. For example, between the 27th and 28th of June, the currents ran an equivalent distance of 26 kilometers, whereas between the 8th and 18th period, the total displacement during that whole time was only 35. It's clear that if we're going to collect the kind of measurements that are needed to formulate a clear understanding of what is going on in these ocean currents, that we're going to need to collect millions of measurements at hundreds of locations in the ocean in a systematic and simultaneous manner. Together with the collection of these measurements, physical oceanographers are going to have to reformulate their attitudes towards the kinds of questions they pose when examining ocean currents.
It looks then as though the collection and interpretation of data to support any theories of the overall circulation of the ocean is going to be a very long and expensive business. And there are many more problems to be tackled. How the water masses of the ocean get mixed up is at the moment very poorly understood, and so is the dissipation of tidal energy and how it affects general or detailed water movement. And although we can see a clear correspondence between surface currents and winds, we don't understand how the wind sets up currents any more than we know how the wind transfers energy into the waves. All this may sound like an esoteric playground for mathematicians, enough puzzles to keep them happy for years. But as man's activity in the deep sea increases for defense, for recovering minerals from the seabed, for waste disposal, for fisheries research, understanding currents is going to matter a lot.